Hello everybody, this is Royce Abel here with the Autodesk Simulation Technical Support team. I want to thank everybody for joining. We have sort of a different presentation today than we normally do that Todd will be leading us through. And basically it's a happy holidays from the Autodesk team here. And at this point, we also have James Youmatz joining us, and he's the ex-Little League MVP. Todd today is the self-proclaimed comedian. And I am the retired rowing beast. And yeah, hopefully you enjoy the presentation.
All right, guys. So the first thing that I wanted to do is let's go over what we're going to do for today's discussion. This should be quick, but I'll leave it up to you guys. Basically, I'm going to do a quick, hey, look what I did. And then we're going to let you guys call the shots for the rest of the webinar. So I respect that it's crunch time and everybody's trying to get out of here before the holidays, but wanted to get together and at least give everybody a quick shout out. So here is a little fancy rendering from CAD of, I don't know if you guys have ever seen these before. It's a German centerpiece. I think it's called a Carousel centerpiece. Is that right, Royce?
Yep, that's right.
And essentially you have a candle that burns and then it spins there, and it's a pretty neat little thing. And I was like, I'd seen one of these done in CFD before back in the CF design days, and thought I'd resurrect it and make it a little bit fancier because our computers are a little bit more higher powered these days. So quick rundown of how I did it is very similar to the way that you should approach every engineering problem. I took the minimal that I needed for the geometry and brought that in to do my tests for the physics and figure out where I'm going to have some problems. You know, if I'm going to have meshing issues because of the way that I had created some of the geometry, at least I don't have very detailed geometry that I have to troubleshoot while I'm figuring it out, and I can get some of the mesh settings and anything that I need to do with the physics, because this is actually a fairly complex problem. I'm running a heat source causing buoyant flow, and then running with flow-driven motion. So by all means, not the simplest of analyses to set up, and the more troubleshooting I can do on something that runs faster, the more likelihood I'm going to have success in the end. So then I wanted to show you guys this guy. So this is a VTFX that I exported from CFD, and here I can move it around and zoom a little bit differently, and if I wanted to, I can pause it and step through. Of course, I didn't pause at the beginning. Let's do play. And
so what Todd's just trying to show here, what a lot of people forget, that there actually is a plugin for PowerPoint and Word where you can go through your design reviews and things like that and show live CFD results within your PowerPoint without having to go back and forth and make it a little bit more seamless in how you present that at work.
Yeah, so the first thing I wanted to do is actually, I'm going to check with you guys and see, did you guys know that this was available? So I've always thought that this is actually one of the cooler features, that you can put this into a presentation and you're not sitting there with the software live while you're talking to your boss and a bunch of people that don't really know CFD, and then they're pinging you for, I want to see this result or that result. It's already locked as what's available, and you get to show exactly what you want to show. You can say, I can get back to you with any of those questions.
Okay, and right now we got about 75% of the people have voted, and a resounding 78% of people said no. So I definitely encourage you to check it out and give it a try. It can be a little quirky at times when you first learn because some of the navigation is a little different. since it's a plugin and not native within the tool, but it can be very powerful and handy.
The best place to get the plugin is actually from the Cetron website, and that's CEETRON. They're the ones that created the VTFX format files. I'm gonna hide that poll. But yeah, funny thing, Royce probably doesn't even know this. So when I was first demoed the software over a decade ago, and I saw this plugin with just the faucet demo model, I was like, I'm going to go work for these people. That's incredible. So that is by far just one of the coolest things that I think is really underutilized, because yeah, it gives you a lot of power. So then let's actually show you guys the model. So fairly simple setup. I have an air domain that I then have a relatively, this is the more complex geometry after I've figured out how to get everything to spin. For boundary conditions, I have heat loads on my flames. And if I look at my air, I just set this up as a pretty simple chimney model where I have zero pressure and temperature down at the bottom. Not completely 100% realistic. I probably should have done it more of a bucket, but I thought I could save myself some mesh and get some initial results and have something fairly decent to show you guys, and could always tweak those other settings. Again, that's something, if I really wanted to dive into it, that's where I would be playing with the simpler model to verify that my air domain is going to work before I kick in the full geometry, because this guy takes about a day to run.
Yeah, if anyone's ever done the bucket approach, it definitely comes with extra troubleshooting.
Yeah.
So chimneys are easier.
Yeah. By all means, it's a good way to start, even if it's not 100% applicable, because you can always tweak from there once you know you've got it running. As far as the mesh goes, I meshed the air domain. I suppressed the majority of the parts in here because I don't really need them. This is a rotating region that I have. It could be meshed better. And then I have all of my little figurines meshed, and my my little post going up to my blades meshed. This is all one part. So another just quick tip here for if you're doing natural convection analyses, what I did was I put in a region, and it's not showing that I have the mesh on it right now.
That's okay.
But I put it above there just to make sure that I can capture that plume of velocity, because that's really what's driving the whole analysis. If I can't get that velocity profile right, I have no chance. Line mesh sizes, ignore. Yeah, that's fine. Oop. I wanted to say no. So then when I go into my results, you know, just by looking at the global results, if I want to take a look at pressure, and set this guy to part, grab this guy, I can see where I'm actually getting the pressure coming in from the candles that's going to cause this guy to spin. And here if I show my cut plane, oh, I had it in clipping. Didn't even remember I did that yesterday. Planes. Clip. Bring that guy back. Outline. Oh, I know. I want the plane as shaded, but I want the volume as outline. This one doesn't look like the may not be the one with my better mesh.
That's okay.
But yeah, you can see as I'm looking through the model that I have my velocity coming through there and going through my rotating region, and then yeah, going through driving my analysis. If I go back into just looking at this guy as shaded, that, and we can do an animation. This is not one that's spinning. Let's check my other one. I have a lot of these models, so this wasn't the easiest of tasks. I got to feel all the pain that you guys do regularly while trying to get this up and going.
What was probably your biggest pain point, Todd, as you were going through this? Todd basically worked with James last week to put this together, and we wanted to do a different model and share something that we created ourselves that everyone can, or a lot of people can probably relate to. And he went through a few different things that got him frustrated, that's for sure. So don't think that he got through this without, you know, a little bit of anger moments for Todd.
Yeah, this was not as clean and easy as you would have thought. And I guess that actually leads me into, as I promised I was going to let you guys kind of drive the presentation. So I will launch our next poll. And see what you guys are feeling. If you want me to dig and drive further in, you know, Royce was curious about what the biggest pain was. Some people may be interested in results, and I know it's a busy time of the year, and if everybody wants to go, I can let everybody go really early on this one. I really just wanted to get everyone together. And
yeah, so we can easily fill up the hour talking about where people would like to talk about. So Rob asked a question to start off with here, where, you know, there's chimneys and there's buckets. And chimneys, yes, you're going to get a little bit more flow because the air can come in from the bottom. Chimneys, or buckets, on the other hand, only have a opening, a zero pressure on the top of the normal cube or cylinder that envelops your entire model. So because of that, you know, the airflow's got to come from the outside edges of the bucket, go through whatever is driving the flow upwards, in this case the candles or flames, and then the plume will go through the middle of the opening. The tricky aspect of the bucket models is because you have air going in and out of the same surface, and that the flow really needs to have that balance and sort of extra complexity of the flow sort of flowing back against itself. It can be a little bit more unstable just because of keeping that balance. And usually what it is that if you have a decent enough mesh around the edge of the model, and if you remember that region Todd showed above the geometry of interest, in this case the carousel, then that plume stays much more stable. If that plume isn't stable and staying where it should be and starts sort of oscillating a little bit, then that bucket flow balance becomes unstable and the whole thing will diverge. So that's really the key part there, Rob.
Yeah, Rob actually asked 2 follow-up questions for us.
Sure.
He asked, you would never have openings on the side, and he also asked too many unknowns.
Yeah, generally it's too many unknowns. There's at times, so I hate to use the word never. There are at times I'll use like an upside down T type of shape on the profile view to get something working. That is very difficult. It's actually a little bit more difficult, but it has certain scenarios where that becomes useful. I can't think of a good example right now, but it usually has more to do with more of a mixed convection approach, where the flow rates are much higher, or you have like a fan somewhere in there that's causing a little bit more turbulence. So you might extend those upside down T very far away on the bottom side along the tabletop, so that there's more of a disconnect between the inlet and outlet. The problem with that is that top surface still has a tendency to actually have an inlet and outlet profile. So it becomes more of a balancing act of how you develop that.
Right, how small those are going to be.
Yeah.
There's a whole bunch of, it gets very complicated very quickly.
Yeah, it ends up being more of a guess and check scenario where you give it a try and then you change your external air domain. But yeah, then the thing that goes back, it does become too many unknowns sometimes, and you start getting this sort of cross flow across the T. So.
All right. I shared the polls. We had a pretty good percentage of people. Sounds like a couple people are going to hop out. Thanks for joining us. Happy holidays from Autodesk. From everybody that wants to hear, it looks like you guys want to know how painful my life can be when I have to do your jobs.
Okay, so we're talking about troubleshooting. Yes.
So let's go and start with the geometry. The first error that I hit was a meshing error. And that was coming from this geometry, because really, while I'm getting going, I just need to see, you know, what the analysis is going to do. Am I going to fail based on this simpler geometry? I'm probably going to have issues when I make it more complex. So I just tried to mesh it, and sure enough, it failed. So it failed on surface meshing. What's that? Oh, I can just hide that. Appreciate it. So I had started with this simple geometry where I don't have the candles or any of the complexities around there that I might end up with some issues. All of my ornaments are down to just a cylinder, so I can see if it's going to rotate. And initially I ended up with some meshing errors. And James and I could never figure out. James, you want to hop in on this part of the conversation?
Your poll is also
It's still up. Share, hide.
Do you need to share your screen again, maybe?
Share monitor 2. That screen.
Yeah, there we go.
Okay.
That's weird.
So, quick run through of what I just said. This was my initial model where I just needed some kind of volume to put a heat load on, and I don't have anything really fancy about my blades. I wanted to see if I could have multiple parts in my rotating region. So, if I look at what's going to be my ornaments, I wanted to see if something's going to spin and if I can have it as a separate part, or if I need to merge all of the parts together. Those were a bunch of the initial questions that I knew I was going to be answering. And then my meshing failed on surface meshing for starters. So I was looking around and I saw these little kind of tick marks on the blades. And I asked James, he didn't initially know what caused it, and I don't know if we ever completely figured it out, because it's really just a couple of fairly simple pieces of geometry, a rectangle and a cylinder that's going to be hitting it. But if you see what happens when I highlight here, there's these hidden surfaces. So it took me a little while to find them, but I had to remove those. That was probably my first nasty thing that I had run into. And what I was hoping is I could use a simple rotating region, just make a cylinder that encapsulates just the top of my blades. And then what I found out was that because I don't have the rotating region down here, I would end up with holes in the mesh as it started to rotate. And I was like, well, that may not cause too much trouble, but I should probably do a real rotating region that encapsulates everything that's spinning. So making my rotating region became a little bit more complex. Then I started to run into errors with my rotating region peripheral nodes, and solver exiting unexpectedly before I could get to iteration 1. So I had to do some cleanup on my rotating region, and from there, I finally got to start iterating, and I got to figure out my time step size, because, yeah, I chose something that was too big to begin with and diverged. I chose something that was too small, and I couldn't really get it to ramp up in a reasonable amount of time. You know, I don't want this to run for 2 weeks. I need something as a faster turnaround. So I ran into those problems. James or Royce, what else was I complaining about last week?
You had divergences. I kind of was answering questions, so I wasn't hearing everything you were saying.
Gotcha.
Did you talk about when the sort of hockey puck shape was kind of coming in and out when the rotating region wasn't all around it?
Yeah.
Okay.
Yeah,
that was kind of funny. Somehow that's still the, let's see here. We tried using recap at one point, or 123D. I don't know if anyone is aware of that. So our original goal here was to take a 3D rendering, basically, not like rendering, but 3D reality capture with a tool called 123D, or Recap 360, of the actual carousel, and we discovered that was a little bit too, or this was a little too detailed. And James took about 200 photos of this to try to do that. And then the idea was to bring that into Fusion or Sim Studio to then build around that, as kind of reverse engineering it. And that didn't quite work as planned.
If I could just comment real quick, it definitely, I'm not sure if your guys' workflow, you know, ties too closely into that reverse engineering aspect, but one of the biggest reasons and difficulties that we found it was hard was, and we'll show you a picture of what the carousel really looks like in a little bit, but the biggest issue we had was it got the outside dimensions fine and really captured what it looks like from the outside. But there was just so many places I couldn't stick the camera to really get, if you can kind of picture a behind the scenes view of the middle of the carousel. So realistically, I just had a very cylindrical shape with no hollowed inside, which was the biggest problem that we ran into. And, you know, like Royce said, this was a really detailed model to try to, you know, reverse engineer, but again, with just a camera phone. You know, I definitely think it's a doable workaround, and you know, as far as this goes, it was such an evenly spaced out model that it didn't take too long to model in CAD. But besides that, yeah, I really personally think that the reverse engineering technology is 2 thumbs up.
2 thumbs up.
Yeah.
Cool.
Here's another one. My rotating region, I don't know why this happened, and I think it was just because I grabbed a surface and offset it, and then I tried to pull a couple of different edges to generate this top piece. And you can see that it broke it into 4 pieces. So I was getting a solver exited unexpectedly because of that. So I ended up going back to my geometry. This isn't the final one that I ran with, and I had basically deleted all of the top of this and put in a new cylinder and reattached everything.
Can you hide everything but the rotating region? Right-click, isolate. Yeah.
James is
So
better.
that's the rotating region. Okay, so the rotating region needs to encompass everything that is,
Sorry.
that's gone. Everything is rotating. So as Todd said earlier, he tried to just cover up the blades at first. And there used to be this weird trick where if the rotating region was touching a solid, it would then also rotate that solid.
If meshed solids were touched.
Yeah, meshed solids were such. So if it kind of like broke through the rotating region.
Yeah, what you used to see is the housing for a pump would spin, is how we would spot it. So you're like, this looks absolutely ridiculous. My housing is going all over the place. And I was like, can I use that to my advantage?
Right.
No.
Todd then went back, changed his rotating region so that it encompasses even the shaft that connects the 2 layers that rotate with the actual fan blade that actually are driving the, in this case, it's technically turbo machinery.
Yeah.
Okay. So, So that's that. So there's a few questions. Let me address some things that came in. So there was a note about element types. You know, are we ever going to have, this is more general, are we going to have different element types to make meshing more flexible? Flexible is a little bit ambiguous of what you mean by that. Tetrahedral is going to give you the most flexibility in terms of meshability. If you're talking about flexibility of mesh elements for solver strength, you need to consider what type of solver you really have in the background. So our CFD tool is a finite element analysis program, meaning that it solves at the nodes of the elements. And there's other commercial CFD codes that do the same thing. There's also commercial codes that do finite volume analysis, where you're solving for what would be considered the fluxes of the faces of the elements. Now, if you have a tetrahedral element, that's going to limit how many faces you can basically interchange material through that volume. So that's why you'll see, for instance, hexahedrals used in other codes, because they increase the faces, which gives more flexibility to the directions that flow can go. With our CFD code, we solve the nodes. So in reality, we want nodal points. So if it's a tetrahedral, hexahedral, the hexahedral actually doesn't really help us in terms of solver quality. That's my understanding, at least, without being a solver programmer. So in terms of our code, it doesn't really matter. We do have more than just tetrahedrals, though. We also have prism elements or wedges. That's actually what defines the elements along the walls of geometry, and Todd can show that. So I hope that answers your question, Artur, about the tetrahedrals and things like that. So we have explored that in the past, and just hasn't been necessary.
Oh, I have mesh enhancement turned off on this guy. It's rotating. Oh, when I kicked it to.
Okay.
I wasn't terribly concerned. It saved me mesh and got me to run a little.
One thing to be aware of: there was a mention from Scott about the CFD2 solver in 2017 beta. You will see, if you ever use the CFD2 solver, that we actually use tetrahedrals along the wall elements. So that'll be a change. So prisms will kind of go away and everything will be tetrahedrals. There is also, if you use extruded mesh, then of course you're going to have more of an extruded element. You're welcome. I'm glad that was helpful. Let's see here. So Scott, you can probably answer this one for Ali. I still don't understand why users cannot see the total pressure as a simulation is running.
What? Oh.
I can take this too if you want.
So if we go into result quantities, we have these other available variables that we could see. And essentially, when we're checking these variables, they're an end calculation instead of a calculation that's based on everything else, because that's actually calculated from the other variables. So it's something that we can display, and we just don't have the display available because it would slow down the solving process. Is that?
Yeah, it's basically that. So some of this might be driven more on legacy than anything else. When
Sure.
machines were slower, we're passing a lot of information with every iteration that's solved for on your desktop computer. And if you have more result quantities being passed from the solver to the UI, everything will slow down. So initially, only a small set of the key values like velocity, pressure, and temperature are actually shown live. And then everything else is shown after the fact, just for speed's sake and efficiency of data processing. If you were to extrapolate that out to like CFD2, where you're trying to be as fast as possible across multiple machines, if you have more data processing, data passing, that's going to slow everything down. So our goal is to try to make the solver as fast as possible. If you can't see everything while it's solving, you know, that's a cost benefit right there.
Yeah, a lot of people complain that it runs too slow, and then you'll have people that want to see more, and it's always a tough balance.
Okay, there's all sorts of questions coming in, so this is great. We showed the rotating region. Are you not meshing the pine tree and snowmen? Please explain how you suppress them and yet could visualize a rotating region, a rotating motion.
I did actually mesh them, but that's something that I could actually, I don't know how to get the view in the right angle so I can hide this.
You might need to hide the outside air domain and then get to that one. You're trying to, yeah, now do that. Yeah.
Okay. So now when I'm looking at these are actually all meshed solids. And they're separate parts from the post itself, which this was actually a very nerve-wracking thing for me to start with, because every time, you know, most of the time when you're doing a rotating region, you have an impeller or a single piece that we're really worried about. So I did mesh all of those. I could actually have them as not meshed. You know, you could see before that, you know, I had a view saved where we were showing parts that are suppressed. I can do that by making them visual here, and then they're actually shown by color. So I can decide what color I want to show things. Where's my little candle, guys? There they go. Not all of them. I've got my little candle holders. I can make all of those viewable. One thing that I wanted to point out, because I got pinged on this by several people, the convergence plot here looks absolutely crazy. When you're doing natural convection, you usually get this bump up in the temperature because we're going to heat up the air locally at the flame. And I'm actually curious. I don't think I checked this. Let's check my temperature. Awesome. Look at that. I guessed at my heat load. That was another thing that I had some problems with there, is I was seeing temperatures going really high. I pulled some, you know, just did some Googling for how much heat is coming out of a candle. And I saw that it was between 500 and 600 degrees Fahrenheit, depending on your candle. And somebody had said 15 watts, roughly. I think right now I have it running with either 5 or 10. I had to tune that value. That was another one that I had to tune to try and make it look a little bit more realistic where I'd buy the results. But yeah, first off, the way that the physics work to drive the, you know, the relatively odd shape for the temperature line, it's going to heat up, that's going to change the density, and then the air is going to move. So this is something that we very regularly see in a natural convection analysis. So now, this thing's diverging, right? Look, these lines are going up and down, and it's completely crazy. How could you trust that? If I really look at what those lines are, the blue and the pink, that's Vx and Vz. So Y is going to be my main flow direction, and Vx and Vz are really just kind of going to be, that's something that I don't care about too much. If it's fluctuating, that can be due to geometry, it can be due to numerical error, it can be a handful of things. And before I'm really going to buy into this, I'd go and I'd take a look at Vx by itself, and I see that this is bouncing up and down and seemingly getting a little bit crazier. But when I isolate it in the convergence plot, I see it's from 0.5 to negative 0.5. And that's actually driven by your geometry units. So that's in millimeters per second. So this is varying at the end by 1 millimeter per second. When I look at my overall velocity being over 500 millimeters per second, and the way that I always double check that is I know natural convection analyses. Typically you're running about 20 inches per second, anywhere from really 10 to 60. So when I see that number, I feel relatively okay about it. But if that's 550 millimeters per second, 1 is going to be negligible. So that was one of the things that scared a handful of people, and you'll see that the same thing exists in VZ. So even though you've got something seemingly crazy, and we do have rotating machinery, so I somewhat expect that averages can be moving while doing this. The other thing that I think a couple of people might have caught on to is that my animation this is the problem with having sharp viewers instead of some managers that don't know what's going on.
What? Man, that was a quick jab.
Got to get it in there while I can. So, you know, I started with this thing not rotating, and then it ramps up. So I don't have a very even time step, and I don't know if you noticed right there, it looks like it changed directions in rotation. I can go through and I can look at my rotating region results and make sure that my RPM is positive. The problem is that basically we're looking at snapshots at different points in time. And it's just like a car going down the highway. You look and it looks like the rims are spinning the opposite direction. The same phenomenon is going to happen here, where your eyes are tricking you into thinking that it's spinning backwards, and you have to see it here, and it's just because that I chose a relatively poor time step for my save interval. I tried to fix that a couple of times. Usually just continuing from the end is the easy way to do it, and I was struggling with that a little bit, where it was trying to restart.
All right, so got some more questions in here. Can you go over the assumptions you made on the flame? And it may not have been a deep assumption, but you need to look up Google in terms of how much heat is output from a flame. What do you assume for the material?
So for the material, I actually just used air for this analysis. A lot of times we'll use a resistance. One of the things that's a little bit goofy is once I made the resistance be a little bit fancier of a shape, you know, we're defining a resistance in the X, Y, and Z direction, and when I had it come up to this point, it made the resistance act a little bit goofy, so I just changed it over to air, which isn't a terrible assumption because I know that most of a flame is actually air. There's nothing to really hold that heat there. My heat load, again, I went into Google and I found a guy that made radiant heaters from a candle, and that's where I saw the 15 watts and the temperatures. And I figured as long as I was relatively providing something similar to that, then it would be fairly valid. The other thing that we did here, this is where I set up. I didn't set my decision center in this one.
What did the actual cross-section look at that? So are you doing? What the flame looked like in the like a temperature profile on the plane here?
I could do that.
I was kind of curious myself.
This is my crappy mesh one. Let me go to the other one. And if you guys were wondering what the design differences are, I actually rotated the blades by 15 degrees. And when the blades are turned to be more flat, let's verify that. Not setup parameters, review, rotating region.
I think it's like 22 RPM or something, 23.
This one's 23, and when the blades are flat, it comes out to 20 RPM. So by opening that flow and, you know, giving it more of a torque, I actually sped it up. Just for
Where's the flame?
Come on, flame. Well, I'm almost there. Maybe not.
Right.
Am I dragging this the right way?
Oh, you weren't.
That makes more sense.
There we go.
I saw one. And you can see my, right now you can actually see where that region is above it to capture that airflow. I'm getting close because I can see my velocity heading towards the flame.
There it is. Okay, outlet mode maybe. Here we go.
Oh man, I'm awesome. Nope. Come back. What did I do?
Hit the, go to global and do it.
Just do this one.
Yeah. There we go.
Let's do shaded. Oh, because it thought I was selecting the plane.
Right.
So there's my velocity, kind of to be expected where it's highest at the tip. We look at the temperature. And then let's set this to part.
Oh, you're animating.
Oh!
There's a bug. Don't set the part during an animation.
I don't know if that's true, actually.
Really?
This computer is struggling very. It's got problems, to be nice to it.
Yeah, we had to reformat his laptop about a month ago.
And it's still not. So as soon as I close the PowerPoint, I'll show you this. When I close the PowerPoint, I get 2 errors. There's another assertion error, and then I get a Microsoft.NET error. It's awesome.
Okay. So a few more questions coming in here. Are you considering a converged solution with the Y velocity, temp, and pressure only due to rotating regions in the X and Z plane?
Relatively, yeah. I'm looking for this because if I actually go back and show you what I did for my rotating region, this is a free spinning rotating region. So what I'm really interested in is how fast is this spinning, how much torque, all of those things are really what I'm trying to figure out. Because my design change was moving the blades, but I could be possibly just leaving the blades in the same orientation, but moving them higher, where maybe my air velocity has already picked up a little bit more, being further away from the flame. You know, that would be another possible design change. And what we want to see is the velocity, so, or, you know, the rotational velocity of our whole carousel. So once I see that that's been relatively hanging at the same point and my VY isn't changing, then I know that I'm sitting at a relative steady state.
Yeah, and Robert Smith had a good suggestion too. You can put some monitor points in like the plume area or some other region.
Oh yeah.
You can just monitor the primary flow direction until you get, you know, your oscillatory flow
right
going. Or to see that plateau, depending on what you're looking at.
Right.
Okay.
That's a very good suggestion.
Very good suggestion, Rob. Let's see here. So Rob had a good point. We had a little discussion going on in the Q&A in the background here about suppressing solids and things of that nature within the rotating region. So if your solid is meshed, then that mass will be included in the rotating region. Technically, if you suppress all those, then yes, you lose your mass in terms of the inertial effects in the rotating region. But what you can do at that point is go into the material properties of the rotating region and define what the inertial mass is to compensate for that change. Okay, and you can get that from your CAD package base at that point. So yes and no, there's some disadvantages. So I guess earlier when I said there weren't any, yes, there are, just as long as you're aware of when you do suppress the outcome of the inertial mass.
Right.
Okay.
And again, that's going to come across as an assumption, and as long as it's an even assumption behind all of them, that's another one that I actually did here, was I just picked an inertial mass versus really calculating it. I knew I wanted it to have a reasonable amount of resistance. It probably should be higher, but as long as it's the same between my designs, I get to know which was the better design.
Interesting, Scott. No, I've never heard that suggestion before yet, and about basically having the legend being driven on where the mouse location is. So if you were to hover over a flame, that would change the legend based on the max and min values of that part and kind of dynamically move. It's interesting.
So like do a set apart based on
mouse location,
the location of what I'm doing. That's kind of cool.
That's kind of cool. I like it, Scott. I'll throw that in the idea station if I were you. Let some people vote on that one. I think that'd be kind of cool.
Yeah.
I don't make assumptions on too much demand on resources. I let the programmers decide on that, and Heath, the project manager, or product manager. Make as many suggestions as you want. I would vote for that one. Let's see here. At this point, things are sort of wrapping up when it comes to questions. I believe we have gotten to everything. I'm just looking back here. Got to the tetrahedral one. There was one question I missed here from Liliana, but she has left about giving examples of modeling buildings. We do. Unfortunately, today we don't have anything prepped, but to answer the question, yes, we do. And we'll have to do a webinar on modeling buildings in the future. That's a hard one just to pull out. At this point, is anyone else any more questions? We should be unrelated complaint from Mike. Why aren't global units global? Thanks, Rob. Global units are, to me, global is false advertising there on the result task. Global,
about the difference here.
Yeah. On the far left here, when you go to global, and then you right-click and go to global units, to somewhere off the window. Global results really are going to show your surface or skin quantity or state for whatever you're showing. Okay. Or if you were to create an isosurface or a new plane, it's going to default to that unit because that's the global kind of unit at that time. So yes, it's a little bit confusing. And does that answer that, Mike? So yes, I would agree. It's kind of a nuisance sort of. Mike wrote yes, ... So I think him and I are on the same page. But as long as you know what it means, you end up being okay.
Yeah, I don't know.
Can you initiate a steady state solution first and converge before starting the rotating region portion? Maybe that would ease time to convergence on the rotating region portion. Yes, you can technically do that. Well, no, you cannot actually do that. You could do a quasi-transient / steady state solution where you lock the actual rotating region from moving, or put it at a very fixed low RPM and allow the flow to develop, and then allow it to rotate. But you can't have a rotating region material assigned in a model and then run it at steady state. The solver won't let you do that.
Yeah, it knows that it has to be a transient solution.
Yeah, there's some basic checks there to make sure you're not doing something that you shouldn't. Okay. So at this point,
I'm going to kick it over to James to be the presenter.
So at this point, I just want to thank everybody for joining. James right now is trying to show his webcam from his laptop. We'll see if that works. We're having some issues with this earlier, so please don't leave yet. How to set time intervals. Thanks for asking a question to burn some time. Time intervals are set within the solver dialog. You can set the intervals for saving intervals, or you can set to save basis for the summary file. And you can set up a table as well to drive how often you save those intervals. Just be careful not to save too many. More recently, I tried to limit that to about 20 or 30, depending on the size of the model, just because you end up getting way too much data within the actual design study, and sometimes that can really bog down performance. So how is through the solver dialog, and there's a little caret or arrow that kind of expands the solver dialog down so that you see some extra options. So findability isn't super easy unless you know it's right there and you notice that that line is there to do that.
Actually showing up.
Okay, so any other questions? All right, so we're having some difficulties with the webcam. Basically what we were going to show is the actual carousel rotating and leave you on a high note. Apparently we've run into technical difficulties with GoToWebinar that will not allow us to get to that, so I apologize for not getting to what we wanted to show. It's all good. So again, I want to appreciate everybody for joining. Todd and James had a lot of fun putting this together. It's not too often where we get to sort of start from scratch and feel all your pain points and send that over to development. And just want to say Merry Christmas.
Yeah.
Happy New Year.
Happy holidays, everybody. Thanks for joining us. I know this is the crazy time of the year, so yeah, let's finish up strong and
take a break.
Yeah, yeah. Enjoy time with the families.
Yeah. All right, everybody. You have a good one. We'll catch you at the New Year. Bye-bye.